In this next section, I want to show how the LCP array that I'll define brings back more flexibility from what the suffix tree could do to the suffix array world. And those two together will basically be able to replace what we had done before in the suffix tree. So that's maybe a little less obvious. So to motivate that, let's see what you remember from this long list of applications of suffix trees. And specifically the one algorithmic problem I used to motivate back then to study suffix trees in the first place. This longest repeated substring or longest common substring, remember they are quite closely related. The longest repeated substring is the cleanest technically. So what did we use that, especially our, what are all the features that we used in suffix trees to get that? Yeah, I think I set it up. There's really just one answer that's the key thing. So if you just want to know the length of the longest repeated substring, you only really need one thing from a suffix tree. I probably should have included an option. I don't remember anything at all. But in case of doubt, maybe you just have to guess one for this one. Okay, waiting for 25. Do we get 5 more? 2, 3 more? 1 more? I think it already clicked by the time this makes it through the network. 25, as I guessed. And you still can't see. Now it's coming. Well, I can show you the right answer here as well. So what I had in mind is the string depth of the internal nodes. And just to remind you, if we are trying to find the longest repeated substring of a given text of a string, we can build the suffix tree, compute the string depths of all the nodes, and then the path to that node is this longest repeated string, but the length of it is just the string depth. So in this case, we had this one at depth 3, right? But there was another one, no, this one, which is also at that depth. Right. How are we supposed to do this with a suffix array? All we have is this sequence of leaves. So if we just have the suffix array, it seems not really possible. It doesn't contain the relevant information. We can do it by storing the relevant information on top of the suffix array. And that will be the LCP array. LCP stands for longest common prefix. And it will be the longest common prefix of 2 neighboring leaves in the suffix tree, or 2 neighboring entries in the suffix array. So I want to point out here that we usually define the LCP array other than our other arrays. It starts at 1 because it talks about the difference between 2, and so there's some offset in one way. I have a bigger example on the next slide. Maybe let me just illustrate this. So if I take the suffix array of this string, I should just follow the leaves left to right, right? That's what we get. 957316084 and between any two adjacent ones I can define this LCP array. So it would really want to sit here with a number between every pair, so something like this. But of course we don't define our arrays with an offset of 0.5. So stored as an array, this is 0, 1, 2, 3, and so on in the suffix array. And for the LCP array, we start with 1. So the longest common prefix is between r and r minus 1. But we use the leaves in sorted order. So it's the entry at 1, if we do this here as a concrete example. So LCP of 1 is the longest common prefix of two suffixes, namely the one starting at L of R. L of R is 1, so that's the text starting at 5. And of L of R minus 1, that's 0. So it's L of 0, which is 9. Okay, so if I map that to the tree, so I would look at this, and I would ask, what's the longest common prefix between you two guys? And remember, the longest common prefix is the string depth of the lowest common ancestor. There was a thing with a box around it at the time. Last time I said, memorize this. If you did, then you may recollect it now. So in this case, it should be 0. They don't share any common prefix. One starts, well, I guess T9 is just the dollar, right? So you always get 0. Okay. Maybe one more less boring example between, say, 5 and 3. So this entry, LCP of 3, sorry, 7 and 3. If I go up to this one, I should have a string depth of 2. So LCP would be 2 in this case. Okay. Now, if I have the LCP array, the longest common prefix is actually trivial to find. Let me fill the array just so that we have this. And it's relatively easy. You just follow the traversal of the tree. 1 and 6 is 0. 6 and 0 is 3. 0, 8, they go via the root, so that's 0. 8, 4 has depth 1. Those is this node, it's depth 2. Else, finding the length of the longest repeated substring is just the maximum entry in the LCP array, so 3 in this case. There's more. So I motivated it from this longest repeated substring. But indeed, a lot more about the suffix tree is encoded by suffix array plus LCP. And again, mostly on an example, but I think that makes it clear. Here's the suffix array. Here are the suffixes in sorted order. What the LCP array is about is the longest common prefix of adjacent suffixes in sorted order. And so you see here, these share an A, but then they differ on the next position. These share AN, then they differ, and so on and so forth. And where there's nothing, they don't share any common prefix. As on the last slide, just vertically now, the LCP array should be thought of sitting between the entries of the suffix array. And so the numbers here are just the lengths of these red strings. And now I can do something called LCP intervals, which is tracing tracing ranges where this common prefix starts again with a common prefix. Let me make it clear on an example. The entire range is spanned by the epsilon LCP interval. Everyone starts with the empty string. So all the suffix, or all the suffixes start with the empty string as a degenerate case. Then there's a range of suffixes that start with an A, namely these 4, and their longest common prefix between this and this, this and this, this and this, they all start with an A. So we have this range of length 3 here that covers from here to here all the strings. They all start with an A, and there's a similar range for things starting with a B and starting with an N. Now within the range of all the things that start with an A, there's another range, namely this one, of all the things that start with AN and then something else. All right? And similar for the other things. Now, if you remember the suffix tree for this example, because I've shown you probably 500 times, you may recognize this. There's a one-to-one mapping between the internal nodes of the suffix tree and these intervals in this longest common prefix space. So the root corresponds to the all-embracing interval. Everything starts with nothing. There's a node here that corresponds to this interval with A's, containing everything in its subtree that starts with an A, and so on and so forth. The connection to just the LCP array is a bit more subtle, but in the numbers, you can see any contiguous range that has at least a 1. So in this range, the LCP values are always at least 1. They never drop below 1. In the entire range, they never drop below 0, well, by definition. In this range, they never drop below 2. So the ranges are defined by ranges where the value doesn't go below a certain value in the LCP array. And that corresponds one-to-one to the nodes of the suffix array, suffix tree. We won't dig much deeper onto this. I will leave it with this example and the intuition behind it. But I hope that it's maybe enough for you to believe that with enough algorithmic ingenuity, if you just have the leaf array and this LCP array, you can get the rest of this picture. The information is all there. It's maybe not quite the most convenient form, definitely not for humans, but it's all there. So these two are enough to reconstruct the suffix tree. And in fact, they're enough to simulate everything you can do on the suffix tree directly on these arrays. The last bit I want to talk about is how to compute this LCP array. Because that's another really cute algorithm and has one more a nice application of amortized analysis. I want to point out, we'll have a tutorial question where you're asked to do this reconstruction. And so maybe you can gain a bit more insight into that just from doing it on another example. The key thing about the LCP ranges is it's contiguous ranges where the LCP value doesn't drop below a certain threshold. And so the string depth of the node is that threshold. In the last section of this unit, I want to talk briefly about how to compute the LCP array. Again, efficiently is our focus, so linear time is the goal. Let's first look at what you can do naively. You could just compute each entry from scratch by its the longest common prefix, so you take your two starting indices of the suffixes and just compare how many characters are equal. Again, as almost always, some text with just all A's will have lots of common prefixes, so you always spend linear time in the worst case, and quadratic overall. So that's not good enough. However, it might be good enough if your text has almost no self-similarity. The insight to get faster than that is if we see one large LCP value where we had to spend a lot of time comparing, we will always see more large values that use the same common prefix. So we can somehow reuse that work. Before defining this more concretely, let me show you one of my favorite English examples. The valid grammatical sentence, buffalo, 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 buffalo. You can go much longer than this. 7, 8, 9 buffaloes in a row. I think you can still parse that as a proper sentence with contact clauses and so on. The trick is there's a city buffalo, there's the animal buffalo, there's the verb to buffalo someone is to bully someone. So you can, in this case, construct a sentence out of a single word. I chose it because it has lots of self-repetition and self-similarity. If you start by computing the suffixes of this text in sorted order and start computing some LCP values, you can find really long LCP, longest common prefixes, and large LCP values because the text has a lot of overlap. Now, if you have these two suffixes, there will be two other suffixes where these first characters are deleted, and these are written here. So they will also have a really longest common prefix because they share all but the first of these 19 characters. And you already know that. So you don't want to start from scratch comparing for this next one. The tricky bit is it's not so clear where are these shorter suffixes and where is the LCP value that you are trying to infer from this. And in a way, it gets worse than that. It's not even clear if there is any LCP value for this. Because these two shorter suffixes might not be adjacent in the sorted order. Once you chop the first character off, there might be other things in between. And then there is no single LCP value corresponding to those two suffixes. But still, it's still somewhat true, right? Even if there's things in between, they will also share this longest common prefix. So that's the key idea behind exploiting it. To turn that into an algorithm, the smart way to do it that Kasai et al. Came up with is to just compute the LCP values in a convenient order, and then all the complication goes away. It's another. I love this one because it's so simple to present, but each time, if you don't have an example prepared, you probably forget how it worked, and you have to reinvent it. So we'll try to compute the LCP values in text order. That's why I have our favorite picture here again. In text order means I'm trying to compute the LCP values corresponding to the suffixes top down on the left, but I will jump around in the actual LCP array on the right while I'm doing that. And so in this case, when you drop the first character, you may not have adjacent suffixes, but you can still use the information you learned from the previous phase. Let's see the example. We'll first look at the entire text. That's the first suffix in text order. I'm starting at index 0. I use my R array to map that to the right-hand side. So I know I'm at position 6 in here. So I'm looking at the LCP, the longest common prefix between that suffix and whatever is just before it in sorted order. This is the relevant LCP entry that I'm looking at. And this one I compute naively by comparing characters. So I find B matches, A matches, N matches, then there's a mismatch. So the longest common prefix is 3. So far so good, nothing smart happened. I remember though that while I will lose the first character, this AN, I will keep that in mind. If I go to the next suffix in text order, it will start with AN. It has to, because I know the previous one started with BAN. But which LCP array entry am I finding now? I look at the rank array, and that brings me to this position. So I know I'm looking at this suffix and whatever comes before it in alphabetic order. And I already know it has to start with an. Why? Again, because I previously compared with this one, and this one without the B started with an. Find this here. Now, it's not the one that I actually compare it with, but all of these strings have an as their longest common prefix. And so in this case, it happens what the previous slide said. There was another suffix that's smuggled between the two. But if it ever happens like that, the longest common prefix has at least this an. So what we do in this case is we inherit the two, but then we start comparing the next character, because there could be a longer match, as in this case. But then there's a mismatch. So again, the LCP entry we find is 3. And we keep in mind that we found NA. We keep in mind that we found 2 apart from the first character that matched. And then we continue like this. We go to the next position in the text, find where are we in the right-hand picture, down here, rank 9. So we're looking at this and this, and we already know without thinking they have to have at least 2 in common. In this case, these are exactly the 2 suffixes, so we kind of know that they already have just these 2 and no third, but we forget that. We just do another comparison and compare B and N again and find they're still not equal. But this little rediscovery is cheap because it's a single comparison. So we find another LCP entry, and we remember there was 1 overlap still after removing the first character. So when we go to the next position in the text, which we find over here, then we can inherit 1 character that matches, and we find 1 more. All right. I think now you get to see the pattern. We go to the next position in the text, find where that is on the right-hand side. We inherit 1 match, and that's actually the only match there is. It's again a case where we have exactly the 2 suffixes without the first character. So we have a new LCP entry, and this time we don't remember anything anymore. And then the remaining ones, this one has LCP 0. They don't have anything in common. These 2 have not anything in common. These 2 have 1 thing in common. So we have a 1, and this is a 0, and that's it. So you see how things, maybe you can already see you always just spend constant time in each iteration. You inherit a variable number of matches, and then you may spend time in one iteration, but then many other iterations become cheaper. If you write that up in code, it looks like this. I don't think there's anything worth pointing out. So we remember in L, what's the length of the prefix that we already know about? Initially nothing. Then we go through all the positions in the text. We find our way on the right. That's the mapping to the right. We find what is the other suffix that we compare with, which is the one just above it in sorted order, but we have to find it in this way. Then we compare the characters that are equal, but we leave out the first L comparison, the first L characters in both strings. We store what we found, and we set L to be 1 smaller or 0. And then we continue. If you analyze this in terms of the number of character comparisons, counting how often we compare 2 characters, the way to go in this case is to count separately how often you find a comparison where the outcome was equal and how often you find an outcome where it was not equal. Because then the not equals always terminate the loop. We'd only do the character comparison at this point. That's the only place. So that's the only cost that we are interested in. How often do you iterate this loop over all the iterations of the outer loop? Every unequal outcome jumps out of the while loop And so we have at most one of these for each iteration of the for loop, at most n. Whenever we have an equal outcome, we increment L. So far, that's all we can say, but L can be at most n because it's a length of a common prefix, and it's only decremented by 1 once for each of the outer iterations. So we can decrement it at most n times. So overall, it can only be incremented 2n times in the worst case, and probably less. So for both of the outcomes, we have a bound in terms of n, so the overall cost is linear. If we have the suffix array and the LCP array, both of which we can construct in linear time, as you've seen just today, we can actually reconstruct the suffix tree from that if we wanted, using this construction with the LCP intervals. But the key message should rather be, you don't want to do that. You don't want to compute these two arrays to compute then the suffix tree from that and spend all that space. The modern version is use these two arrays and maybe a few extra tricks. So probably you want L, R, and LCP, so 3 arrays to be fair. And use those to replace suffix arrays entirely, suffix trees entirely. So that's what people now call enhanced suffix arrays. They're a little trickier to build algorithms for. So usually what people do is design an algorithm as if you had the suffix tree, and then simulate access to the suffix tree based on the suffix arrays, enhanced suffix arrays. It turns out you can actually do everything that suffix trees can with these arrays, and they use much less space, and it's much simpler to construct them. Mainly the reason because you can split it up into building first the suffix array and then the LCP array and then stuff on top. Whereas the suffix tree seems to be, you have to solve everything to get everything at the same time. No summary, so let me do that verbally. That's the end of the string matching chapter. I like this as I like this best among most of the modules because it brings us very close to recent developments. There are a few quite deep parts, but we've cracked one of the black boxes open that we started with. We know how to construct a suffix tree in linear time now, at least the theoretical ideas behind it. And actually we found something better. The suffix arrays can do all, so in practice you would not really want to compute the tree in the first place. And so you can use that to build a relatively small data structure for a huge text and very quickly find occurrences. I didn't say, so one thing that this, for example, contains is finding the occurrences of a pattern in the text. You can get rid of this log n factor using tricks on the LCP array that we didn't get into, but it's one of the things that is possible. And all the other fancy applications of suffix trees you can also do. But that's beyond the scope for this. I hope you enjoyed some of the constructions. And so that's all I want to say about text indexing.